Now, for which inputs is the average cost defined, and give a real-world explanation for this. Well, my average cost, again, was 45x plus 550 divided by x. It's defined for x being greater than 0. We cannot have x equal 0, and we're not going to produce negative units. So a real-world explanation of this average is the average cost is defined for x greater than 0 because you wouldn't produce less than 0 items, and the function is undefined for x equal to 0. If nothing is produced, it does not make sense to discuss the average cost. Since it was so hard to read the writing that I just did, here is that answer typed out. So it's actually readable and you can copy it. Let's to graph the average cost function for 0 to 5,000 roses, which is 50 units since each unit is 100. What can you say about the average cost? The average cost function. So that was 45x plus 550 divided by x. Sell less than 0 items. So it said to do 50 units. I'm going to have less than 0 costs. Put this at 1,000. It'll make a more interesting graph. And that is the graph for the average cost function for this problem. What can you say about the average cost? Well, as the number of units produced increased, the average cost decreased. Now we need to talk about composite functions. The composite function f of g is defined by f of g. Notice this is an open circle, not filled in like a multiply sign, which is defined by f of g of x equals f of g of x. The domain of f of g is the subset of the domain of g for which f of g is defined. So we want to look at the domain of g as we're trying to figure out the domain of the composite function. The composite function g of f is defined by g of f of x equals g of f of x, and the domain of g of f of x is a subset of the domain of f for which f of g is defined. We'll work some problems so this makes a little more sense. The composite machine can be thought of as the composite function machine can be thought as a machine within a machine. The composite function machine, in which the input is denoted as x, the inside function is g, and the outside function is f. So the composite rule is denoted f of g, and the composite function output is symbolized f of g of x. Note that for most function f and g, f of g does not equal g of f. They're not necessarily equal. So we basically put the g function inside the f function is what this means. So we have the following functions. F of x is 3x minus 1, g of x is 4 minus x squared, h of x is 1 over x, and give the domain of each new function formed. Well, here we want h of f of x. So h of f. Sometimes this one's the understand. We're going to start with the h function, 1 over the x, and the x in this case is f of x, 3x minus 1. So this is the function, and the domain, well, we know when we have a fraction that 3x minus 1, the denominator, cannot equal 0, so 3x cannot equal 1, and x cannot equal 1/3. And in interval notation, that would be negative infinity to 1/3, or to positive 1/3, combined with starting with 1/3 to infinity. This would be the interval notation. Now we're going to f of g of x. So f is 3x minus 1, and in place of this x, we're going to put g, which is 4 minus x squared. So it'll be 3 times g is 4 minus x squared, and then don't forget the minus 1 from f of x. Simplifying this, 12 minus 3x squared minus 1, or negative 3x squared plus 11. This is f of g of x. The domain, well, the domain for a quadratic function is all real numbers. So that was fairly easy. G of f of x. We said they meant not necessarily the same thing. So we start with g of x, 4 minus, and then in place of x, we're going to put f of x. So minus 3x minus 1, the quantity squared. That will give me 4 minus 3x minus 1, so square the first term, 9x squared. Multiply 3x times negative 1 is negative 3x, double it, negative 6x, and negative 1 times negative 1 is plus 1. Now I need to remove the parentheses, so 4 minus 9x squared plus 6x minus 1. This becomes g of f of x will be negative 9x squared plus 6x plus 3. And again, it's a quadratic function, and these were a linear and a quadratic, so it's defined as all real numbers is the domain. Technology note: if you have two functions, the input as y1 and y2 on your calculator, you can enter the sum, difference, product, quotient, or composition of these two functions as y3. These combinations of functions can then be graphed or evaluated for input values of x. So let's look what happens. The sum. Well, if your new function, y3, would be y1 plus y2, and that's what you'd enter for equals y3 on your calculator. Different, you would make it y3 equals y1 minus y2, depending on which order they ask you to put it in. The product, y3 would equal y1 times, and that's a little asterisk on our calculator, y2. We want the quotient, y3 would equal y1 divided by y2, and your calculator will automatically do that. Composition, y3 equals, y1 is the outside one, y2.